In this video, you will learn how groundwater, streams, and springs support the hydrologic cycle in a watershed. Groundwater originates from rain and melting snow that flows through the soil and into the rock below. The saturated rock area is called an aquifer. There can be several different groundwater aquifers in any given area. Aquifers may be separated by dense layers of clay or rock that don't allow for easy movement of water. These areas of clay and rock are called aquitards. Springs often form where the downward movement of groundwater is limited by a layer of clay or dense rock, causing the water to move sideways and emerge along a hill slope. Springs often form the beginning of streams. Groundwater aquifers also provide most streams with a constant supply of water that upwells within the stream channel. This constant flow of groundwater to streams explains why very few streams dry up, even after many days without rainfall. Over 1 million rural farmers and homeowners in Pennsylvania use water wells that are drilled or dug at various depths into groundwater to provide a water supply for their farm and home use. This picture shows a typical stream in a forested watershed in central Pennsylvania during low flow in the fall. Hydrologists refer to these low flow time periods between storms as base flow, when the flow in streams is dominated by groundwater. During these base flow time periods, the quality of the water in the stream is greatly influenced by the type of rock underneath the watershed's surface. For example, watersheds with lots of limestone will have streams that are less acidic than watersheds dominated by shale or sandstone. Groundwater entering the stream during base flow conditions has often traveled a considerable distance and time underground before reaching the stream. Some of the water may have only traveled for days, but other flow paths can take months or even years. Hydrologists can use various methods to age water in the stream to determine approximately how long ago it fell as rain or snow. Penn State studies of several small forested watersheds have found that the water flowing during base flow in these small streams was, on average, from rain or snow that fell 1 to 5 years ago. Here we see the same stream in a much higher flow condition after a heavy rainstorm. Notice how clear the water in the stream is despite the high flow. That's because the roots associated with the dense forest and understory vegetation hold the soil tightly in place and prevent erosion from causing sediment to enter the stream. Also, the dense roots and especially the old decayed root cavities provide many holes in the soil called macropores, where water can be easily transmitted through the soil to the stream. Thus, soils in forested watersheds act much like a sponge, absorbing large amounts of water, filtering out sediment and other pollutants, and allowing the downward movement of large volumes of water. Macropores are pathways that may be formed by existing or dead roots, insect holes, or small mammal burrows. In a forested watershed, the soil is interlaced with a dense network of macropores, which maximize the amount of water the soil can absorb and transmit to groundwater and to nearby streams. The ability of forest soils to absorb and move water is most easily seen through measures of infiltration. Infiltration is the rate at which water is absorbed into and through soil. It is usually measured in inches of water moved per hour. An infiltration measurement can be done by pouring a measured amount of water into a watertight ring installed on top of the soil and measuring how long it takes for the water to infiltrate completely into the soil. If this experiment is done on undisturbed soil in a forest, infiltration rates in excess of 15 inches per hour are commonly measured for dry soil. As soils are disturbed or compacted, the loose structure and macropores are lost, causing a reduction in the infiltration capacity. For example, a typical residential lawn might only be able to infiltrate 1 inch of water per hour. It is most important to compare this infiltration capacity with the typical rate of rainfall for a given area. For example, if there's a lawn that infiltrates just 1 inch of water per hour, and there's a heavy thunderstorm that dumps 2 inches of rainfall in 1 hour, it's expected that about half of the water will run off from the lawn rather than infiltrate into the soil. But the same storm in a forested watershed would not produce runoff, since the rainfall rate is still far below the ability of the soil to infiltrate water. Since infiltration rates in forested areas are usually much higher than any natural rainfall rate, we would expect all water to infiltrate in the forest and none to run off the surface. Based on the high infiltration capacity in forest soils, some storm precipitation does not even reach the soil because it is intercepted and evaporated from the canopy or the leaf litter layer. Precipitation traveling through the forest canopy can become throughfall, which is water reaching the forest soil, or stem flow, which is water draining along stems and trunks of trees. As throughfall and stem flow reach the soil, they quickly infiltrate into the soil and groundwater. So even during heavy rainstorms, the increased water in the stream is not due to water flowing over the surface. Instead, nearly all of the increased water in the stream occurs from water moving through the soil or groundwater. What little precipitation does make it directly to the stream does so by directly falling on the stream channel, which is referred to as channel precipitation.